Thank you very much for the introduction and for the invitation. Yeah, so my title was towards a p-adic Deligne Lusztig theory, but I think this is a better title and is less misleading. And the reason I say that is because all of my representations will be over QL bar, not QP. And the p-adic refers to the groups whose representations I'm studying. Okay, so to start off, I want to maybe just give a brief introduction to classical Deligne Lusztig theory. So this began in a 1976 paper of Deline and Lusztig. And so the setup is that first I take G, a reductive group, over a finite field with a Frobenius F. And I'm going to take G to be the FQ points. Okay, so the main goal of Deligne Lusztig theory is to understand what the representations of this finite group are. And so we can begin by just trying to construct a class of representations by our hands. So what's the easiest such class is, well, if I take T inside G to be a maximal split torus, then I can choose a Borel containing it and let U be the unipotent radical of B. And from this, what I get are principal series representations. So let me just remind you what those are.
Are you choosing T inside the FQ points?
The FQ points. OK, and how are these constructed? Well, T is a torus, so it's abelian. So its representation theory is very easy. All the irreducibles are just given by homomorphisms to QL bar star. And B surjects onto T. So this means that given any character over here, I can pull it back to something on B. And so what is the principal series representation corresponding to this? Well, this is just the induced representation. Oopsies, let me tell you what I'm inducing, of this character theta, which, let me remind you what the definition is. This is just all functions from G to QL bar, satisfying the following relation. That if I take f of GB, then I pull out a theta acting on B. Okay. But the kernel of this map is U. So what this means is that if I have such a thing, then U is acting trivially. And so this is just the set of functions on G mod U to QL bar, satisfying f of GT now, because that's the only thing I have to keep track of. OK, so I get this. OK, but now what is this thing here? This is some finite set. And so this is, and so finite sets, so I'm going to put a C here for later use, but it doesn't make a difference here because it's a finite set. With L-adic coefficients. This is H0 of this thing, and it's a part of H0. And what part is that? Well, this G mod U is a finite set where G is acting on one side, and T is acting on the other side. And so this space that I wrote down of here, this space of functions, this is precisely the subspace of this zeroth cohomology group where T is acting by theta.
What is theta?
Theta is this character here.
Oh, you just choose some character?
Any character. Yes. OK. So right, so this constructs for us some class of possibly not irreducible, but some class of representations of G. But the issue is that for a reductive group over a finite field, not all representations arise in this way. So the question is, how do we get the remaining of them? And so that's the question that Deligne Lusztig theory answers. So what we can do is we can upgrade this picture. In the following way. Okay, so over here we started with T, a maximal split torus. And so the example to keep in mind is just the diagonal matrices inside GL2FQ. Okay. But there are other maximal tori inside GL2FQ that are not conjugate to this one. And so one can hope that you can upgrade this picture to something that somehow can accommodate any maximal torus you'd like. So an example of one that is not covered on the left-hand side is the non-split torus FQ squared star sitting inside GL2 FQ. Okay. So in fact, for GL2, these are the only two possibilities for maximal tori. Okay. So what did we do up here? Over here, we took this G mod U, and this was a finite set of points. So that's a zero-dimensional variety. And on the right-hand side, what we can put over here is we'll put some smooth affine variety. And this thing over here, like on the left-hand side, should come with the left action of G and a right action of T. So the actions commute. Okay. So how do we use this to obtain a representation of G? Well, we looked at the subspace where T acts by some character. And so that's why, so over here we had this over here. So every time I write a cohomology group that doesn't have coefficients, it'll always be QL bar. If it's not QL bar, I'll tell you what it is. Then it'll still be an L-adic sheaf. Okay. On this side, what I want to do now, if I have a variety now, it could be bigger than zero-dimensional. And so I just look at the cohomology groups. Okay. Okay, so how can we, what is the picture of what these things are like? So I just want to describe what the picture is, and then I'll give you the actual definition. So this G mod U sits over G mod B, and this is a T torsor. Right, there's nothing too mysterious there. But I can rephrase G mod B in a different way, which is G mod B is the set of all flags F of FQ bar, the two-dimensional vector space over FQ bar, such that if I apply Frobenius to the flag, I get the flag again. Okay. But then what is this saying? This thing is equivalent to saying that F and the Frobenius of F are in relative position 1 to each other. And this 1, I'm viewing this 1 inside the while group of GL2, which is just W2, which is S2. And so this consists of two elements, the identity and the non-trivial one. Okay. So I'm going to try to repeat a similar thing on the other side. And so this Deligne Lusztig variety right here, this is going to be a T torsor over some part of the flag variety, and this is going to be all flags F such that F and the Frobenius of F are in relative position W. Okay. But then this is we can unpack this a little bit. What is this? These are the sets of elements of P1 such that if I take the line given by V and I take the span with the line given by the F translate of it, this thing is the entire vector space. Okay, so in other words, this is P1 of FQ bar minus P1 FQ. Okay, and in this setting, this thing right here, this is equal to set of xy and FQ bar such that x, y, x to the q, y to the q, the determinant of this is not an FQ cross. So this is the vanishing locus of xy to the q minus x to the qy. The q minus 1 equals to 1. No, so this is an extra condition. Yeah. If it was FQ bar cross, it'd be too big over this. Yeah. Okay, so this you may have seen before. This is something called the Drinfeld curve. Okay, and that's the I would say the simplest instance of a Deligne Lusztig variety. Okay, so let me tell you what happens in general. I start with G, a reductive group over FQ. Again with Frobenius F. I take G tilde to be the FQ bar points, and I take G to be the F fixed points of G tilde, and that's just the same thing as the FQ points of G. Okay. So what I'm going to do is I take a torus inside G tilde, a maximal torus. It's necessarily split. And I'm going to assume that this torus is F stable. So what this tells me now, the fact that it's F stable and it's a maximal torus to begin with, this tells me that if I take T to be the F fixed points of T tilde, this is going to be some maximal torus of the FQ points. But this is not necessarily split. Okay. Okay. Now I take a B tilde, a Borel, containing T tilde and a U tilde, unipotent radical of B tilde. And then the definition of the Deligne Lusztig variety is the following thing. Okay, so it shouldn't be obvious to you why this setup becomes this setup, but this I wanted to just paint the flavor of what it is, and we'll use this definition later. So just sort of take for granted the fact that this reduces to this in those special cases. Okay, so let's look at the actions here. So if I act by G on the left, every element of G by definition is equal to its F translate. So when I put a G over here, then it's going to cancel out with this stuff. So I have a left action of G, and since T stabilizes U, then I also have a right action of T. Okay, so we're in a completely analogous setting to over here, except I just defined a much more complicated object. Okay, so what's the point here? The point is that from this picture, you get a correspondence. And on as an input, we want to put in something easy, some easy representation theory, and get some hard representation theory out. So the easy input is we'll put irreps of maximal tori. So this is I take some maximal torus T and I take some character theta. And out of this, I want to get irreps of G. But yeah, so what is the rule? Well, from a t comma theta, I will spit out the alternating sum of the cohomology groups. X, T, G. Okay. So a caveat here is that these aren't always irreducible. So I put something here. But we do know, so yeah, okay. So let me see.
And why do you have to quotient for that interpolation back?
I think you don't. This will be some affine thing, so it doesn't change the cohomology. But I think it makes sense to put it there from the perspective of coming from flag varieties. So.
What do you mean by the alternating sum? What do you mean by alternating sum of the HI?
So without the alternating sum, each of these things is a representation of G. So what I mean is this as an element of the Grothendieck group of G. So even if I say something like the alternating sum is irreducible, I actually mean plus or minus that thing is irreducible. Okay, so this is the situation where G is a reductive group over FQ. And let me say some things about it. So I told you that these objects aren't always irreducible, but it is true that every irreducible of G appears in these objects. On the right-hand side. As a summand is what I mean. The other thing is that you might say, okay, well, you have this fancy geometric construction of these irreducibles, but maybe there's some like simple way you can do it without using geometry, and there's just no way. You can do it in special cases, but this is like doing this, finding these representations geometrically is the only uniform way of constructing the representations of reductive groups over finite fields. Okay. Yeah, so this, the fact that every irreducible appears inside these cohomology groups.
What do you mean right side? You mean that in the decomposition?
In the decomposition, yeah, it might not appear as a single thing, but yeah.
Could it be that a given irreducible representation occurs in more than one of the cohomology groups?
Yes.
And when you say something, this virtual thing is irreducible, could you write A minus A plus B, and B is the irreducible? And would you call that an irreducible?
Yes, I would call that irreducible, yeah. Yeah, so it's... yeah, so an easy example of when an irreducible appears multiple times is, say, if you take for SL2, then Steinberg will appear in the one where you put a trivial character here, but it appears both where you put the non-split torus and the split torus.
No, but for a given choice of T and theta, I'm asking, you write down
yeah,
cohomology groups. I'm asking if a given representation can occur in two of those cohomology.
And you have cancellation in the the thing. So I think if there was cancellation, I would still call the alternating sum irreducible. But I don't know if it is possible for them to have cancellation. Yeah. Okay. So this, right? So Lusztig used this construction in order to write down all the full character, write down the full character table. Okay, So it is tractable. The other comment is that this construction is actually essential for known algebraic constructions of representations of p-adic groups. So an easy example is that if I take such a thing, if I put, this alternating sum, if I take a situation where this is irreducible, then what I can do is upgrade this to a representation, let's say of G, okay, yeah, representation of, how should I say this? Say I take the situation for GL2, and I can upgrade this thing to a representation of GL2 ZP just by pulling back along the natural surjection, and then extend to a representation of by the center inside GL2 QP, and the resulting induced representation from GL2 ZP to GL2 QP is often an irreducible supercuspidal representation of depth 0. Okay. Tied in with this is that these have what I mean is constructions where they say, oh, you induce the following way, and then you extend to a bigger group in the following way, then you induce again, rather than saying, here's a variety, it comes in the cohomology. So that's, I didn't mean it in some official way, yeah. These things are also related to affinoids in the Lubin-Tate tower. And this was done by Yoshida. Okay. Okay. But similar constructions have also been done for in other settings. So one could ask, well, what if I want to change G? I don't want it to be a reductive group over FQ. What can I do then? Are there analogs of this, and does it give us new information about representation theory? So say we again start with G, a reductive group over FQ. One thing we could do is consider GR of FQ, which is defined to be this kind of thing. So this would be like the characteristic P analog, or you could take the Witt ring. Okay, so such things have been studied by Lusztig in this first situation, and then extended to the general case by Staszynski. But one can also do other things. So on the spectrum of adjectives for groups, reductive is on one end and unipotent is on the other. And there have been some isolated examples of Deligne Lusztig type constructions in this setting that have proved useful to p-adic groups, which I will explain. So this. Okay, and then finally we come to p-adic groups. So say you take a reductive group over a non-Archimedean local field, so I mean QP or a finite extension of it, or FP paren T, or a finite extension of it. Then there are multiple things that one can do here. So there's something called an affine Deligne Lusztig variety. And these things are analogs of the classical Deligne Lusztig theory, except that instead of G over a finite field mod B over a finite field, you take G over a p-adic field and you mod out by a hyperspecial, for instance, or you mod out by Iwahori, for instance, or something even deeper. So this is something deeper in the Moy-Prasad filtration attached to the Iwahori. Okay. So, but there's also something else here, which was pioneered by Lusztig. The semi-infinite Deligne Lusztig variety. And this takes G, a p-adic, and it's kind of related to G mod B over a p-adic field. So this is a wildly behaved object, but the hope is that certain parts of it can be studied. So there's some relation between these two pictures. At least for GLN and its inner forms. And this is my joint work with Alexander Ivanov. But that's the subject of another talk. Okay, so. Okay. So, outside of this top board, everything over here is not very well understood at all. But the upshot is that any progress you make in any of these three situations likely has some implications in the p-adic setting, which I hope to explain now. And so, yeah.
I mean, is the aim here to recover all supercuspicals through some construction?
The grand goal, yes. Yes. Okay. So let's take K, a non-Archimedean local field. G, a reductive group over K with Frobenius F. This is the maximal. This is the completion of the maximal unramified extension of K. Okay. Oh, I shouldn't have erased this definition here. Okay. So this should be familiar. I just erased this and I will rewrite the same definition because the definition Lusztig proposes in the p-adic setting is exactly the same as the classical setting, except all of the groups you replace with their p-adic counterparts. So what is the conjecture here? Okay.
What's the F? That's Frobenius. You're not in characteristic P, apparently.
I'm not in characteristic P.
Yeah.
I still have a Frobenius, right?
Extensions of Q cover.
Are cut out by.
So this thing
Yeah, this is just a set. This is just a set. Yeah.
Frobenius just generated of the color because you had an R with
What? Yes.
Oh, okay, that's just a set.
This is just a set. But this just a set still has an action of T and G.
So is G just the K points of the
G is just the K points of the group, yes. So, which is the same as the F fixed points of G tilde. So here's the conjecture. The first thing is that this set can be endowed with some algebrogeometric structure. But not just that, we want this to be an algebrogeometric structure over FQ bar. Okay, just. So this, if one can do this, this is going to be a giant object. This will be an infinite dimensional thing. Further, the conjecture is that one can define some kind of p-adic homology of this that's functorial with respect to the actions of T and G. And you also want smooth representations coming out of this. Okay. So assuming that you can do this, what one wants to do is that for any given theta, a character of T, we want these cohomology groups to eventually vanish. And further, if theta is in general position, we want this hi x theta to be concentrated in a single degree. Okay.
Why do you expect the X to be a scheme over FQ bar rather than K unramified?
You don't, well, if you want to get all the representations, you want to be taking, the homology groups that you get, you want to be very large, right? Because, unlike in the finite field setting, like these are going to be infinite dimensional representations. So it's a pseudo answer. Okay. Okay, so from now until the end of the talk, I'm going to specialize to the following case. This is when G is equal to a division algebra of invariant 1 over n. So this invariant 1 over n is just for simplicity, but division algebra is definitely.
Sorry, Charlotte. There's some degenerate case where you have a split torus or something.
Yeah.
This would actually just recover G mod U.
Yeah. Well, I want anisotropic.
Oh, I see. Okay. So you don't want to. Okay.
I don't want to. Yeah. If I take it.
It kills my complaint.
Okay.
What is this conjecture true in real n?
Right. So let me say what is true. Yeah. Okay. So let me. The short answer is yes. Yeah. So how do I specialize the right hand side setup to this thing over here? So that's not so clear. And so what I need to tell you, I'm going to start with this. And I need to explain to you what the Frobenius is. And so this Frobenius is going to be this kind of twisted thing. I take this element, then I attack G coordinate-wise with my Frobenius. And then I twist again by this element. Okay? And so if I take T tilde to be just the diagonal torus, then what this setup gives me is that my G will be this D cross, and my T will be L cross, where L over K is an unramified degree n extension. Okay. So in this setting, 1 is solved by Lusztig and Borisenko. And in fact, this is the only case that 1 was solved. So really, like this, this is an extremely serious obstruction to working on this conjecture. But
What does it look like? How do you make this?
yes, I will tell you what it looks like. Yes. Given that 1 is solved, now 1 can try to answer 2. So let me write down a theorem. Now, the main theorem. For any smooth. Okay, so for any smooth character of my torus, there exists only one place where this cohomology group is concentrated. So this is actually stronger than this over here, right? This is saying if it's in general position, then you expect it to be concentrated in a single degree. But in fact, in the case of division algebras, this is just true always. Okay, and now we have to try to understand what this representation is. So let me try to describe it to you in a way that you have seen before. So I take this theta first, right? And let me assume that theta has, let me assume that it has trivial Galois stabilizer. And the reason is that this theta is a character of L cross, which means by local class field theory, we can reinterpret this as a character on the V group of L. So that means that I can induce from the V group of L to the V group of K this character times a rectifying character. And this condition right here, that theta has trivial Galois stabilizer, is saying that this thing is now irreducible. This is irreducible and of dimension n. Okay. Now, local Langlands tells us that from this I can associate, I think this is usually called this, a supercuspidal representation of GLN. So this is LLC. And Jacques A. Langlands will tell me that I can take its transfer over to an irreducible representation of D cross. And this representation is precisely this.
Let me just repeat my question. So you start with a division algebra relative to GLN because what is easier there? What's true there?
You mean why is one easier in division algebra than GLN? Yeah. So yeah, there's kind of an accident that happens. That I'll explain when I tell you what these things look like. And it has to do with the determinant, essentially. Yeah.
What is the characterization of local Langlands that you're using?
Under this, Okay. Yeah. Well. Yeah. Let's talk afterwards. Yeah. But maybe I should say which representations you occur here. An intrinsic definition. I mean, an intrinsic way of describing this class. So. Okay, so this is what it is. Okay. Okay, so let me tell you about one now to answer the various questions. So why is one easier in this situation? So this x, by a calculation, an explicit calculation, can be identified with the following set. Okay. But one can explicitly calculate what this set here is and explicitly calculate what this thing here means. And what this means is that all of these elements are of the following form. Such in G tilde, such that the determinant of this is fixed by Frobenius. So this should feel kind of familiar because this is what we saw the Drinfeld curve as, right? It looked something quite similar, except here in the division algebra setting, I have these pi's down here. Okay, so to answer some of the questions that were asked earlier, what happens in the division algebra setting that is special? Well, up to here, this also works for GLN and its inner forms. But the special thing here is that if I have an element in here that has whose determinant has valuation 0, then all these x1, x2, and x3 have to have been integral to begin with. So if that G is in OK cross, then so this G is inside X, then X1, X2, and X3 had to have been in OK inside the ring of integers.
So we're doing n equals 3 in this example?
In this example, yeah. So, so obviously you can continue in the obvious way that you would think to extend this. Okay, yeah, so I'll put an n here. Okay, so what does this mean now? This means that I can write this as a disjoint union over M and Z of these pieces that are where the xi's are sitting inside this ring of integers. But now I can truncate them so that they're inside some quotient of this, and I get something that looks like this. So where xh has the same form and where, let me write this in the n equals 3 setting, x1 is in WH of FQ bar, and x2 and the rest of them, xn, are in WH minus 1 of FQ bar. Okay. So it requires work, but one can define, one has the following characterization is that if I take the homology groups of these things, so not the cohomology, the homology of this quotiented by the action of the last part. So this is like things that are 1 plus pi to the h minus 1, da da da. This thing naturally embeds inside, oh, wait, sorry. This thing is naturally isomorphic to hi of h, xh minus 1. So what we can do is to define hi of x to be the direct sum of all of these things, where I take this limit over okay. Okay. So my point here is that the definition of the homology group doesn't follow for free once you know the algebraic geometric structure. You first need to understand how the g action and the t actions play in. Say again?
Do you expect that you can do this kind of thing whenever you have an anisotropic group?
I don't know exactly what to. Yeah, I expect something similar to happen in all settings, though the only places I actually have a proof is for GLN and its inner forms. But you mean when the torus is anisotropic? Is that what you're?
Other groups, instead of division algebra, they're still anisotropic.
Oh, still anisotropic. I mean, you can still do something similar to this in GLN. So even for not anisotropic groups. Oh, right. Anisotropic means that you don't have a torus. Right. We have a torus. Okay. So what this tells us here is that if I want to understand what x is, I need to understand what xhm is. But in fact, all these xhm's are more or less the same. They're just shifted by I mean, these are all translates of each other. So the only thing I really need to understand is xh0. Okay? And given that, the only one I really need to understand is something that I'll call xh, which is you take exactly the same definition for x equals 3, n equals 3, the same thing. But now we put the further assumption that x1 looks like this, i.e. x1 is, in terms of coordinates, is 1, the first coordinate is 1, and then so forth. x2 and x3 are in w h minus 1 q bar. So this is really the thing where determinant is an element of this group here. Okay. Okay, so here's the conjecture of Borisenko on these varieties, and it's that for any character chi of the group that's acting, so the full group obviously doesn't act on this, but the part that acts is the subquotient that's given, so GH1, this is a subquotient of G. And then the torus will be a TH1, which I'll tell you explicitly what that means. It means you take the elements that are in OL that are 1 mod, the uniformizer, modulo the things that are 1 mod pi to the h. Okay, so for any chi, a character of this, there exists an R chi such that the cohomology of this guy is concentrated in a single degree. Furthermore, we expect that Frobenius to the q to the n acts on the ith cohomology group by multiplication by -1 to the I, q to the n I over 2. Okay, that may seem kind of random, but what this condition is equivalent to is that this xh has as many rational points as its cohomology can possibly allow it to have. So this second condition is equivalent to saying that xh of q to the n attains its Deline bound. So given that we have this theorem here,
How do we switch from homology to cohomology?
say again?
We had homology there,
Yeah,
and we have cohomology.
and we have cohomology here. Yeah, so for a smooth finite type scheme S, then I define homology to be the cohomology with, say this is pure of dimension D. I define this to be as follows, with a Tate twist. Okay, the theorem is that Borisenko's what? Yeah. Sorry, I said it smooth and pure dimension D. Yeah. Oh, right. Yeah, but in this setting, yeah, I have something simpler. Okay. So what to erase? Okay. Okay, so let me in the last 5 to 10 minutes give some idea of what the proofs look like. Okay. Let me say something about the second theorem first. I call this 2 and call this 1. Okay, so what one can show is that the alternating sum this thing, chi here, for any chi, this thing is irreducible, plus or minus in irreducible. And this is a method, this is by method of Lusztig. Okay. And the second step, so say you've shown this, and say you can also show the following thing, that if you take the Hom space from GH1, the induced representation, let's call this chi prime. Okay, so say we can show that this Hom space from any chi prime to here is concentrated in a single degree. Then what I want to say...
What do you mean a single degree? What degree?
This degree.
That I.
Yes,
There's
this
only
I.
one I where
There's only one I in this sentence, yeah. Yeah, so let's say I equals to R chi. Okay, so what I want to say is that this thing implies that HCI XH, this thing can only lie in a single degree, concentrated in a single degree. Okay, so let me, this simple but not, it may not be immediately obvious, is that say I take pi and it occurs inside this space. Okay. Right. Okay. So say I have a non-zero irreducible representation that occurs inside here for some I. Who knows which I? Right? Well, this thing, that means that this pi has to sit inside one of these, right? Because the regular representation is equal to the direct sum of all of these as chi prime varies through all characters of th1. So right? Okay. So what does that mean? This now means that that xhi being non-zero, this space being non-zero by assumption means that I has to be the same as r chi prime. Right? Because I'm saying you take an irreducible inside here, that irreducible has to sit inside one of these induced representations. But now by this, I know that it has to be inside r chi prime. Okay? But now I know the entire representation, the alternating sum is irreducible. So the fact that I has to only be in this thing means that I can't have cancellation. Right? It can't appear in more than one thing. So if you have an irreducible representation that's coming from an alternating sum, and you don't have any cancellation, there's only one degree that it's concentrated in. So the real technical heart of this proof is in showing this thing. And how does one do this? Well, this can be kind of related to the cohomology of an affine space, which is easy, but with coefficients in a very complicated sheaf. And so what you can do is try to calculate the cohomology of that affine space with a complicated sheaf by doing a kind of inductive process. Okay, so now let me say how theorem 1 allows you to obtain theorem 2. Okay. Oopsies. Okay. So I start with a smooth character. If it's a smooth character, then there's some h for which theta is trivial on ULH. Right? That's the definition of smooth. So you can assume from the get-go that this is the situation. So what this means is if I take its restriction to UL1, then this can be viewed as a character of TH1. Right? And so what do we get then? So by construction, what we have is that the homology group of the infinite dimensional thing, the theta piece, you can analyze this. This is the induced representation from some subgroup that I won't tell you about of this XH chi. So there, you need a little bit more to beef it up to this group using the information of theta, but more or less this is the situation. Then the vanishing statement about where the homology is concentrated in just follows from theorem 2. And 3, well, we need some way to characterize what this representation is. So an application of the Deligne Lusztig trace formula applied to XH allows you to obtain the following character formula. If X is an element of OL cross whose reduction, whose image in FQ to the N cross has trivial Galois stabilizer, then the trace of X acting on acting on the non-vanishing part of this homology is equal to the following simple rule. This is equal to -1 to the r theta, the sum over elements in the Galois group, gal of L over K. Sorry, this is kind of hard. Okay. But once you have this on all such elements, what you can do is use some characterization formulas of NEART to say that this is actually the representation that you thought it was from the beginning. Okay, and so, yeah, so I guess the main point here is that once you have established the first part of Lustig's thing, in this case for division algebras, it's still a lot of work to understand what those things are. So this gives a description of what those representations are, and once you have that, then you can ask, okay, well, what can we say for other groups? And so for GLN and its inner forms, this is joint work in progress with Alexander Ivanov, as I mentioned earlier, and this relates these semi-infinite Deligne Lusztig varieties to sort of infinite towers of affine Deligne Lusztig varieties, where you take this Iwahori and you let the Iwahori go down deeper and deeper in the Moy-Prasad filtration. And so this allows you to get some information about part 1 of Lustig's theorem, and then you can combine many techniques to try to understand what 2 is. But the punchline there is that you should also get this compatibility with local Langlands, Jacquet-Langlands, and all these kinds of things for representations that satisfy this property. Okay, I'll stop there. Thank you.